Alright, now we're going to talk about power series for those of you who have taken a class in real analysis, and for those of you who want to go back and remember their calculus. In some ways, uh, this is actually feeling backwards, because the standard presentation nowadays is that you first talk about sequences, series, power series, and their properties, then in an advanced class or in a real analysis class, and only then do you talk about expansions and Taylor expansions, such as the expansions that we've been working with all along already. This is where Churchill and Brown are very unique, at least to my knowledge, because they're talking about power series after they've talked about analytic functions, and as a consequence what they actually get is a very natural presentation of the various very interesting properties of power series that turn out to be here to be very natural consequences of analyticity of the respective functions. So let's take a look at that, and let's see what we'll get. So now that we know that every analytic function is locally equal to a power series, of course we want to know more about power series themselves. So that's one of the first advantages. We know why we're interested in power series. It's because analytic functions have all these properties, right? Okay, so far we had a function and found it from the power series. We will now, and found from it the power series, there we go. Now we're going to start with the power series and want to know the properties of the function that it defines. So that is a switch in point of view. And it turns out that functions defined by power series are very well behaved, and that is really one of the reasons why complex analysis is so strong, because of course analytic functions are locally equal to their power series. But to prove the requisite results, we first need to take a closer look at the convergence of power series. So we have to delve a little bit deeper into the theory. We'll have to deal with epsilon and delta and all that stuff that we have seen every so often come up. And even though if we're coming straight from calculus, this is something that we're not used to, this is really the heart of analysis. So we might as well get a couple of more examples of proofs that use epsilon and delta. So let's see, what's our first theorem? Our first theorem is we're looking at a power series, and we assume that it converges at the point z1 not equal to z0, and we let capital R to be the absolute value of z1 minus z0. Then the power series will converge absolutely for every z that is inside the circle z minus z0 smaller than R. Okay, and remember, absolute convergence meant that the sum of the absolute values of the terms converges. Okay, so now let's take a look at the proof. Because the power series converges at z1, which means that the power series with z replaced with z1 converges, we know that the an z1 minus z0 to the n converge to 0, and therefore the absolute values converge to 0 also. That was one of the criteria, one of the consequences of convergence of series. If the series converges, then the terms converge to 0. In particular, that means there is a capital M greater than 0, so that all these absolute values are bounded by capital M, because if this converges to 0, then a tail will be small, and the rest you just choose the largest value for your capital M. And that means if we set Q to be z minus z0 divided by z1 minus z0, remember that z minus z0 was strictly smaller than R, so that Q is smaller than 1. Then we have that the sum n equals n plus 1 to infinity. Remember, whenever we talk about convergence, the tail is the hard part, so we're looking at the end of the sum here. So we're looking at the sum n equals n plus 1 to infinity, an z minus z0 to the n absolute value. Well, we're going to do the same thing as what we have done in previous presentations. We're going to expand, so we're going to get a geometric series, right? So this is, we now just have expanded with z1 minus z0 raised to the nth, because we've divided by it and we have multiplied by it. Everything else stayed the same, and we took the liberty to split the absolute values apart. But now we know this stuff out front is bounded by m, so this is smaller or equal than m times the sum n equals n plus 1 to infinity q to the n. And we know that that is capital M. Pull a q to the capital N plus 1 out, and the rest is the sum that starts with exponents 0, 1, 2, 3. So that's then really a geometric series. So that gives us the q to the n plus 1 divided by 1 minus q. And as n goes to infinity, well, m is a constant, 1 minus q is a constant, and q to the n plus 1, because q is smaller than 1, goes to 0, which means that goes to 0 as n goes to infinity, and that establishes the absolute convergence of the series, and that is because the difference between the nth partial sum and what ultimately will be the limit is going to 0. Okay, what are the observations from the theorem and from the proof of the theorem? Well, for every power series, there, first of all, from the theorem, I think we'll also have observations from the proof a little bit later on. Well, we know that for every power series, there must be a number c, so that the power series converges for z minus z0 smaller than c, and diverges for z minus z0 greater than 0. Well, that's not what the theorem says, but think about it. If it converges at a point z1, then it must converge on the disk z minus z0 absolute value smaller than z1 minus z0 absolute value, and that rules out any other shape for the region of convergence. Wherever you've got a point where it converges, you get a disk of a certain radius, and that means once you're outside of the region of convergence, you couldn't get another point where it converges, because then we would get another disk added to the region of convergence. So here we go. Here's z0. Here's z1. We automatically get convergence on a disk. And now suppose that the region of convergence is so that there is a point out here that converges and the rest of the region is in here. Well, that point out here would guarantee convergence on a larger circle. So that means the region of convergence really can't just be something and then other points farther out in a way that is not the shape of a circle. Okay, the number c is called the radius of convergence, very much like in calculus, of course. And the circle z minus z0 absolute value equals c is called the circle of convergence. There are no general theorems about what happens when z minus z0 equals c. That is very similar to what you've seen in calculus, where you get these intervals of convergence and you don't know whether convergence is also happening at the boundary points. So that's not changing, only now we've got a lot more points to deal with. And problems in the complex plane can influence the behavior of functions on the real line. That's one of the really interesting things about that. Let's take a look at the function f of x equals 1 over 1 plus x squared. And we know that that's a power series. That's a sum n equals 0 to infinity negative x squared to the n. And you can, of course, now puzzle that apart. That's negative 1 to the n, x to the 2n. That thing has radius of convergence 1, and that's basically because the geometric series has radius of convergence 1, and that manifests itself on the real line even though there are no problems on the real line. So this is now just talking about the function on the real line. Here's 1 over 1 plus x squared, and here is the 0th Taylor polynomial. Let's look at the second Taylor polynomial. So n equals 2, meaning that that's 1 minus x squared. Then n equals 4, so you get a 4th order polynomial, 6th order polynomial, 8th order polynomial, 10, 12, 14, 16, 18. And you can see that even though the Taylor polynomials are trying to approximate the function better and better, and actually do, the interval of convergence just doesn't get any larger, or doesn't seem to get much larger than from negative 1 to 1 here. In fact, we're never going to get beyond negative 1 and 1. The function just keeps on bouncing around like that, and on the real line there is no reason why this well-behaved function shouldn't have a well-behaved expansion that also approaches the function nicely out here. But if we take the complex viewpoint, we realize 1 over 1 plus x squared has a singularity at I, and it has a singularity at minus I, and power series are limits of polynomials, so limits of polynomials can never give us a singularity and then keep going on the other side. And that means the largest possible circle of convergence for this function really is the circle of radius 1 around the origin. Of course, you can also expand it around other points, but these singularities at I and at minus I will always limit the region of convergence of the power series. And well, now let's take a look at some observations from the proof of our first theorem. The upper bound for the remainder was dependent only on the distance from z to z0. And that's because we had this q equals z minus z0 over z1 minus z0. In particular, however, that means if 0 is smaller than lowercase r is smaller than capital R, then the remainder can be bounded uniformly for all z so that z minus z0 is less than or equal than r. And that means that on such subdisks, z minus z0 smaller or equal than r, there is a uniform minimum speed of convergence because the remainder goes to 0 at a certain minimum speed, and that is what is called uniform convergence, and it's going to be very important for us in the future. So we're going to take a look at that. The power series sum an z minus z0 to the n is said to converge uniformly in the region R. Well, that's unfortunate here, but R is a good name for a region, but it's also the radius. If and only if for every epsilon greater than 0 there is a natural number n sub epsilon, so that for all capital N greater than n sub epsilon, and for all z in the region R, we have that this remainder term is smaller than epsilon. So the only thing that happened here is that, convergence means for every z and for every epsilon, there is that natural number n epsilon, so that for all n greater than n epsilon, we have that the remainder is small. We just have taken the for all z from the outside of this nested quantification to the inside of this nested quantification. And that is very important because now we're in pointwise convergence, as that's called. The n sub epsilon is technically an n sub epsilon comma z because it also depends on z. In uniform convergence, the n sub epsilon really just depends on epsilon because everything else happens for all z inside that region. Okay, the theorem now is if the power series sum an z minus z0 to the n has a circle of convergence z minus z0 equals r, and if r sub 1 is smaller than r, then the power series converges uniformly for all z for which z minus z0 is smaller than r sub 1. Okay, well, let's take a look at that. Because the power series converges at a z1 on the circle. Okay, here's where I need to fix a few things. And we're back. I didn't like my notation there for a minute. Let z sub r be so that a z sub r minus z0 absolute value is r1. So this thing is on the circle of convergence. Hang on. Yeah, thought so. Zr is on the circle of convergence, so Zr minus Z0 is equal to R, and so that the sum n equals 0 to infinity an Zr minus Z0 to the n converges. Wait, can't demand that. Okay, third try, but this one should work. I need my z sub r minus z sub 0 to be greater than r1. We will see why in the proof. And I need that the sum n equals 0 to infinity an zr minus z0 to the n converges. But if I need that, I have no guarantee that anything converges on the circle of convergence, so I actually must put my z sub r so that its distance is from z sub 0 is strictly smaller than r. Then I have that this converges, and then of course now if a series converges, we know that the terms converge to 0, the sequence of the terms goes to 0, and that means in particular there is a capital M greater than 0, so that an zr minus z0 to the n is smaller than m for all n. Remember, this stuff goes to 0, which means on a tail it's all smaller than epsilon to begin with in absolute values, and the first n values you just pick the largest one and you have an upper bound. Therefore, if we set q to be r sub 1 divided by zr minus z0, then we know that that is greater than z minus z0 over zr minus z0, because that z minus z0 was supposed to be smaller than r1. And we note that q is smaller than 1 because zr minus z0 was chosen to be greater than r1. That was that earlier choice. With that, we have that for all z, so that z minus z0 smaller than r1, we have that the sum over this tail of the absolute values a n z minus z0 to the n. That's the sum n equals n plus 1 to infinity, and again we're doing something very familiar. We're expanding with zr minus z0 to the n, which we're multiplying with here and then dividing by here. And we realize that the a sub n times zr minus z0 to the n, those are smaller than a capital M, and the z minus z0 over zr minus z0 to the n, those are smaller than q to the n. And again, we now get that this is m times q to the n plus 1 over 1 minus q with a familiar trick with geometric series. You factor out a q to the n plus 1 and then do the geometric sum. And we know that that converges to 0 as n goes to infinity, and it converges to 0 uniformly. So that means that the power series converges uniformly for all z minus z0 absolute values smaller than r1, and that was supposed to be proved. Okay, well, worked my way through that. Sorry about the repeated hiccups here, but that is the kind of thing that is rather subtle. There are certain things about convergence that we can demand, and there are others that we cannot demand, and that means sometimes we just have to go in between of what we want to bound and what we can't quite reach. Okay, now we can talk about continuity. So suppose the power series sum n equals 0 to infinity a n z minus z0 to the n has a circle of convergence z minus z0 equals r. Then the function f of z, which we define via the power series, that function is a continuous function on the region z minus z0 smaller r. Again, we can't say anything about what happens at r, but we're quite happy that we have it at least inside the circle already. The proof, well, let's first visualize it. Basically, you have your z0 here, you have your radius capital R, and then this is your region of convergence. And if we're now interested in continuity at z, well, then we need to somehow make sure that things work really nicely in a small circle of radius delta around z. And the way to do that is, again, very similar to the previous proof. We will first trap everything inside a circle of radius R1 where we have uniform convergence, and then we're going to do a continuity argument inside a circle of radius delta where the radius delta is so that anything that's closer to z than delta is inside the bigger circle, and that's because in that fashion we can uniformly bound all those tails, all those sums from capital N to infinity. Now let's take a look at that symbolically. We take z so that z minus z0 is smaller than r, and we'll prove that f is continuous at that z, and that will be, of course, the whole proof. We let r1 be greater than 0, and we let it be so that z minus z0 is strictly smaller than r1, which is in turn strictly smaller than r. So a similar spirit as in the previous proof, we've got to shift something in between. And we let epsilon be greater than 0 because, well, it's going to be an epsilon delta proof. Well, then there is a natural number capital N, so that for all z tilde with z tilde minus z0 smaller r1, we have that the sum over the absolute values a n z tilde minus z0 quantity to the n over a tail, so the sum starts at capital N plus 1 to infinity, that sum is smaller than epsilon thirds, and that's because we have uniform convergence on the open disk of radius r1. Now, because polynomials are continuous, and that's something that we do know, there is a delta greater than 0, so that on one hand we want the delta to be smaller than r minus r1. Yes. Well, let's just leave that right now. And so that for all z tilde with z tilde minus z smaller than delta, we have that the difference between the value of the polynomial at z and the value of the polynomial at z tilde is smaller than epsilon thirds. Yes, we can demand that. Give me a quick pause here. Okay, I'm back. You noticed that I had a little hiccup here, and this is something that I had to fix. Let's talk about this again. Because polynomials are continuous, there is a delta, so that for all, and so therefore the polynomial is in particular continuous at z. we have a delta so that for all z tilde, so that z tilde minus z is smaller than delta, we have that the difference between the polynomial at z and the polynomial at z tilde is smaller than epsilon thirds. That can be done. But in order to control the tails, we also need to make sure that z tilde is still in the circle around z0 of radius r1. And that means that z tilde must be closer to z0 than r1 minus z0, because then with the triangular inequality we realize that z tilde minus z0 will be smaller or equal than z tilde minus z plus z minus z0, and that'll then be smaller than delta plus z minus z0, which is smaller than r1. Okay, so then for all z tilde with z tilde minus z absolute value smaller than delta, we have that these z tilde are in the disk of radius r1 around z0, and therefore we can talk about the following. F of z minus f of z tilde, well, that's just the difference in the power series, and we can break that up as follows. That's less than or equal than the tail of the first series minus the difference of the beginnings of the two series, plus the difference of the beginnings of the two series, plus the tail of the second series. That's because now this guy plus this guy would be equal to the first one, and this guy plus the other guy is equal to the second one. And of course we have used the triangular inequality repeatedly to break this up into 3 absolute values and to also pull the absolute values inside the series. And now we can use all this setting up that we've done before, because now for anything that is closer to z0 than r1, and that includes z tilde as well as z, we have that the sum over these tails is smaller than epsilon thirds, and we have by choice of delta also that the difference of the sums over these starts of the series is smaller than epsilon thirds. And so that means overall we get epsilon thirds plus epsilon thirds plus epsilon thirds, and that's epsilon. And that means that the function is continuous, which is what we wanted to prove. Okay, for differentiability, strangely enough, we will first talk about integrals. So take a power series, sum n equals 0 to infinity a n z minus c0 to the n, with circle of convergence z minus c0 absolute value being equal to r. We let C be a contour that is entirely contained in the interior of the circle of convergence, and we let G be a function that is continuous on the interior of the circle of convergence. Then the continuous function f of z being the power series a n z minus c0 to the n, for that function the integral of g of z times f of z over the contour C can be computed term by term, which means I can pull the infinite sum out of the integral, which is something, because it involves limits, that is not entirely obvious at all, and in fact there are pathological examples in which this kind of thing can go wrong. So that means, what does it mean to integrate term by term? Integral g of z f of z dz is the integral g of z sum a n z minus z0 to the n, and then I can take the sum of the a n's out and have left the integral of c over c g of z z minus z0 to the n dz. Okay, the visualization is that here's z0, here's our circle of convergence of radius r, our contour is entirely inside that circle of convergence, and again we want to have some kind of uniformity, so we will use a radius r1, a disk of radius r1, which includes that contour. Okay, the proof, well, we take r1 to be so that for all z on the contour we have that z minus z0 is smaller than r1, which in turn is smaller than r, so again we shift something in between so we can use uniform convergence, and we let epsilon be greater than 0. Well, then there is a natural number n, so that for all z tilde with z tilde minus z0 smaller than r1, we have that the sum of the tail of the power series at z tilde with absolute values moved inside is smaller than epsilon divided by this number here, which is just the integral of the absolute value of g against the arc length. So again, this is, once you parameterize it, absolute value of w prime of t dt. We know that this is a number, and yeah, it's a number. If g was equal to 0, there would be no concern about the theorem at all because everything would be 0. So we can assume without loss of generality that we're not dividing by 0 here. And then, well, then we just take a look at the integral. Integral g of z f of z dz over the curve. That's the integral g of z sum n equals 0 to infinity a n z minus z 0 to the n dz, which is, we can break up the power series into the sum that starts at 0, ends at capital N, and then continues with the sum n plus 1 to infinity. Everything else is the same. Now we can certainly break up these two integrals, and so this sum, and so we first get the sum n equals 0 to infinity a n integral c g of z z minus z 0 to the n dz, plus, and then we have the integral of g of z multiplied with the tail of the power series. And we know how that goes because now we just have to show that this thing somehow goes to 0. And if we look at the absolute value of this integral, that's smaller or equal than the integral of the absolute value of g of z times the sum n equals n plus 1 to infinity absolute value a n z minus c 0 to the n integrated against the arc length. And well, we knew we had chosen the capital N so that this term here is smaller than epsilon divided by the integral over c g of w absolute value d absolute value of w, so against the arc length. We can see now why we made that choice. It's because we need this denominator to cancel against this integral in the numerator, so that's smaller than epsilon, and that's already the proof because now we know that in this representation here, this term as n goes to infinity goes to 0, and that means this integral is actually equal to this summation with n replaced with infinity. Okay, so we can integrate term by term, and that will allow us to prove differentiability, which is really, really strange because remember that we know from real analysis and from calculus, integrability is a much weaker property than differentiability. But let's take a look at that. Take a power series, and of course power series are very well behaved. It has circle of convergence z minus z0 equals r, and we let f of z be the function defined by the power series in the circle of convergence. Then f is analytic in the circle of convergence, and moreover the power series can be differentiated term by term. That is, what does it mean to differentiate term by term? Well, you just move the derivative inside. For all z in the circle of convergence, f prime of z is the sum n equals 1 to infinity n a n z minus z0 to the n minus 1, just as we are used to from the power rule. How do we prove that? Well, we know that for any closed contour c in the circle of convergence, we can integrate f term by term. So let's go ahead and do that. So this is f times 1 essentially. Integral f of c dz is equal to the integral of the power series dz, and that means we can pull out the infinite sum, we can pull out the a-n's, and we are left with z minus z0 to the n dz. But realize these guys are analytic functions, and the integral of analytic functions over closed contours is 0. So this means this is the sum n equals 0 to infinity a-n times 0. And I don't care if you've got infinitely many zeros that you sum, the result is still 0. And so that means by Morera's theorem, which said if you've got a continuous function such that its integrals over closed contours are all 0, then f is analytic in the interior of the circle of convergence. Now remember, that works for continuous functions of a complex variable, but that's what we have here. And that's inside the circle of convergence of f, sure. But that means now that for all z in the circle of convergence, we have that f prime of z is a power series, because we know that derivatives of analytic functions are again analytic, so it's got a power series expansion. And b is obtained via the formula for the coefficients of the power series expansion of analytic functions. So bn is f prime nth derivative at z0 divided by n factorial, which is nothing but the n plus first derivative of f at z0 divided by n factorial. Now we expand with n plus 1, and we get n plus 1 times the n plus first derivative of f divided, or at z0 divided by n plus 1 factorial. And that's n plus 1 times a n plus 1. And, well, that is exactly what we wanted to have, right? Because if bn is n plus 1, a n plus 1, then we just do an index shift, and we have what we wanted to prove. And I don't think, yeah, I didn't include the index shift here. The index shift is k equals n plus 1. Good exercise to work your way through that one more time, either mentally or with a piece of paper and a pencil. Either way will work, but it's just one of those things that ultimately we want to be able to take in stride. So, well, take it in stride, please. And if there is a question, hey, just email me, come to office hours, and we'll work it out for you. It's not that bad. Okay, now we also want to talk about uniqueness of power series, and if you've got a power series sum n equals 0 to infinity a n z minus z 0 to the n, if that converges to a function at all points inside a circle z minus z 0 smaller than r of non-zero radius capital R, then that power series is the Taylor series expansion of the function f about z0. Now that feels rather weird because, of course, applied people and reasonable people would rightly say, well, what else would it be? And I agree with that, but what else would it be is not a mathematical proof. Technically speaking, we go from a power series to an analytic function. For that analytic function, we can compute the Taylor series, and we have to make sure that the coefficients are, in fact, the same. Now, it ought to be that the proof is just something where we have to keep track of which coefficients come from where, and other than that, it shouldn't be too hard, and that is indeed the case. And so here's the proof. The power series converges uniformly inside any circle of radius r1 that is smaller than r. So that means that the power series is analytic there. And that means that the coefficients of the analytic function f of z equals n equals 0 to infinity bn z minus z 0 to the n are obtained via bn being 1 over 2 pi I integral over the circle of radius r1 around z0 f of c divided by c minus z0 to the n plus 1 dc. So these would be the Taylor coefficients here. And that all comes just from the theory of analytic functions, of the theorems that we've proved quite a bit earlier now. But now we realize that our function is the sum j equals 0 to infinity aj. That should be xc here. And now it is. So f of c, we just replace z with c. And then the denominator still, of course, stays the same. And we realize we can integrate that. Well, we can first simplify. That's 1 over 2 pi I integral over the circle sum j equals 0 to infinity aj c minus c0 to the j minus n minus 1. We just combined all that. And that can be integrated term by term also. Even though we potentially encounter negative exponents here, we would just split off the sum with the negative exponents, which is a finite sum. And then we can also pull out the infinite sum because the rest is a power series. So that means this is now 1 over 2 pi I sum j equals 0 to infinity aj integral over the circle of radius r1 around z0 c minus z0 j to the j minus n minus 1. And we've dealt with these things before. These integrals are only non-zero when the exponent is equal to -1, which means that this will only work when n is equal to j, and when n is equal to j, the integral is 2 pi I, which means that we get a sub n here, and that means that the nth coefficient of the original power series is equal to the nth coefficient of the Taylor expansion, and that means the original power series really is the Taylor series of f. And people sometimes also then say that series are their own Taylor series. There is no surprise there. And thank goodness, I mean, that would just not make sense at all if a series would have a Taylor series that is different from itself. Okay, so now let's take a look at doubly infinite series. And we want to say, well, if that doubly infinite series converges to f of z at all points inside an annular domain r smaller z minus z0, absolute value smaller r, with capital R greater lowercase r greater or equal than 0, then it is the Laurent series expansion of the function f about z0. And, well, if we let r lowercase r0 be smaller than capital R0 and let those be so that they're between lowercase r and capital R, Then from the way series work, we know that the sum c in z minus c0 to the n converges uniformly for z minus c0 absolute value between r0 and 0. And the series from n equals negative infinity to 0, I could have gone to 1, but we really are only interested in the uniform convergence behavior here. That converges uniformly for lowercase r0 smaller z minus c0 absolute value smaller infinity. And that's because, well, these are now negative exponents, so this is actually a sum in 1 over z minus c0, and that would mean 1 over r0 is greater than 1 over z minus c0 is greater than 0. And so that means that this is then just turning out just like a power series and has the same uniform convergence behavior inside a disk. And that means that f is analytic for r0 smaller z minus c0 smaller capital R0. And because we can let r0 go to r and capital R0 go to capital R, the function is analytic for all z minus c0 absolute value between lowercase r and capital R. So that means that this thing is an analytic function, which means we can even talk about a Laurent series. And the same proof as for Taylor's series, only that you also have to deal with the negative exponents, shows that the expansion must be the Laurent series expansion. And because we've got uniform convergence of those series, we can pull the bi-infinite series out of the integral. So that, writing out the details of those and making sure that you understand where and how you use uniform convergence is a very good exercise. And of course, that's one of the things we're also here for. So we'll leave it at this and keep going now, and we'll finish out with multiplication and division of power series, because in this fashion we can very often find expansions of other functions. Interestingly enough, we're starting with Leibniz rule about infinite differentiability. If you've got two functions that are differentiable infinitely often at a point z, then the nth derivative of the product g times h is given by the sum k equals 0 to n choose k, this is the binomial coefficient, g to the k's derivative of g at z, n minus k's derivative of h at z, and you notice that this should not be f and g, this should be g and h. Let me fix that. There, now it is g and h. And well, how do we prove this? We do induction on n. Again, that sounds rather natural. Whenever we've got a formula that depends on a natural number, induction is a pretty good idea. The base step is n equals 0, and that's where I would say it's trivial, but hey, let's talk about that. People often like to say something is trivial, but we want to make sure we've got the details. The 0th derivative of gh at z is just gh, and that's the 0th derivative of g times the 0th derivative of h. And that is the sum k equals 0 to 0. N choose 0 is 1, g to the 0, 0th derivative of g, 0th derivative of h. So that means that that really does work out. And now we can do the induction step. The induction step, we go from n to n plus 1, and most likely we're going to use the product rule, right? So take the n plus first derivative of gh. Well, we know that that is the derivative of what we have for the nth derivative, which is the sum k equals 0 to n choose k, k's derivative of g at z, n minus k's derivative of h at z, which is, if we now just use the product rule, this is sum k equals 0 to n choose k, derivative of the first, k plus first derivative of g, times the second, n minus k's derivative at h, of h, plus the first, k's derivative of g, times the derivative of the second, which is the n minus k plus first derivative of h. Now we just have to shift indices to make things work out. So first of all, we break this up into two sums. There's the sum that uses this first term, which is right here, and then there is the sum that uses this second term, which of course is right here, and other than that nothing has changed. And now we shift indices. We set j equal to k plus 1, which gives us the j's derivative here, and if j is k plus 1, then k is j minus 1, and so that means we get minus 1, which is plus 1 minus j. K is j minus 1 here, and if j is k plus 1, well then when k is 0, j is 1, and when k is n, j is n plus 1, so that gives us the first term. The second term we actually leave alone. In order to combine those sums now, we must have sums that start at 1 and end at n, so we split off the n plus the term with index n plus 1 here, which gives us n choose n, because n plus 1 minus 1 is n, g n plus 1 of z, and h 0 of z, plus the sum where we're now only going from 1 to n rather than from 1 to n plus 1, plus the second sum where we go from 1 to n, and then plus the 0th term where we'll plug in k equals 0 and you get this last term split off. Okay, we need a new panel, but we just keep what we've had on the previous panel. This is just a copy of what we had there. And now we want to combine those things, and so we realize in anticipation, well, n choose n is 1, and n plus 1 choose n plus 1 is also 1, so we get n plus 1 choose n plus 1, g n plus 1, h 0, plus these two sums will now be combined, sum j equals 1 to n choose j minus 1 from here, n choose k from here, added, and both these terms have k's derivative of g times n plus 1 minus k's derivative of h, only here it's with k and here it's with h, so that's why we can factor that out. And then we have that 0th term, and whether we use n choose 0, which is 1, or n plus 1 choose 0, which is 1 also, we're okay. And we realize that that is the sum j equals 0 to n plus 1 choose j, j's derivative of g times n plus 1 minus j's derivative of h. That is, well, let's see. It is clear that this guy is the n plus first term, because that's just what we get when j is replaced with n plus 1. It is clear that this guy is the 0th term, because that's what we get when we replace j with 0. The part where people then sometimes say, well, it's a well-known formula, and indeed it is, but it should be a j here. Actually, it was supposed to be a j here, here, and here. That's when I combined the two sums. The cutting and pasting didn't quite work out. But it turns out to be well known that n choose j minus 1 plus n choose j, that's n plus 1 choose j. That's in fact a computation that you could execute just directly with the definition of the binomial coefficients, and it would be another really good exercise. Okay, we move on. And, well, what are we going to talk about now? Now we're going to talk about the expansion of a product. So if g of z is the sum a n z minus z0 to the n, and h of z is the sum b n z minus z0 to the n, if those things converge at all points inside a circle z minus z0 smaller than r of non-zero radius, r greater than 0, then the function f being g times h, that thing has a power series expansion in that circle, and the coefficients of its expansion are Cn being sum k equals 0 to the n, ak bn minus k. And the proof, well, first of all, by the preceding theorem, and also in fact by the product rule, if you will, the product of two analytic functions is again analytic, and therefore it's analytic for z minus z0 smaller than r. And that means for z minus z0 smaller than r, we have that f of z, not h of z, my goodness. Okay, we have that f of z is a power series, right? And we know what the coefficients are from the formula for analytic functions. It's that Cn is nth derivative of f at the center divided by n factorial. And now by the preceding theorem, we can say that Cn being the nth derivative of f at z0 divided by n factorial, that's 1 over n factorial times that big old formula from the preceding theorem, sum j equals 0 to n, n choose j, j's derivative of g times n minus j's derivative of h, both at z0. And now we know these guys are also just coefficients of analytic, or can be expressed with the coefficients of an analytic function. And so this is 1 over n factorial, sum j equals 0 to n, times the binomial coefficient, which I wanted to write out explicitly here, times j's derivative of g at z0 is just j factorial times aj, and the n minus j's derivative of h at z0 is n minus j factorial times b n minus j. That just comes from the formula for the a-ins and the b-ins, or for the aj's and the bj's. Now we realize the j factorial cancels, the n minus j factorial cancels, and the n factorial cancels, which means we get that this is the sum j equals 0 to n aj b n minus j, which is exactly the same as here, only that up here I used the k as a dummy variable. And this is one of those cases where Churchill and Brown are really interesting, because the formula for those coefficients of the product really comes out very naturally here, and without the background in complex analysis, these formulas are a good bit harder to motivate for infinite series, and even harder to prove. Okay, but we've got them, and so now we're actually finishing out with some examples as to how to multiply and divide these things. If we want to expand e to the z over z squared plus 1 into a power series around 0, well, we first take e to the z over z squared plus 1 and realize that that's e to the z 1 over 1 minus negative z squared, which turns out to be, well, sum k equals 0 to infinity 1 over k factorial z to the k. That's the expansion of e to the z, times sum k equals 0 to infinity negative 1 to the k z to the 2k, which is the expansion of 1 over 1 minus negative z squared. And that means the first sum is 1 plus z squared over 2 plus z cubed over 3 factorial, which is 6, plus z to the 4th over 4 factorial, which is 24, and so on, times 1 minus z squared plus z to the 4th minus z to the 6th, and so on. So as we're doing that, yes, we could formally write out the infinitely many coefficients, but very often we're just interested in enough of the early coefficients, because that is what we could possibly stick into a computer for an expansion. So that is why quite a few of these examples and these homework problems along these lines will just ask for the first few coefficients, and then we just have to multiply it out, well, and just collect coefficients just like we did with polynomials. So this is 1 times 1, and if I multiply this 1 with anything else, I don't get a constant term anymore, and I don't get constant terms from here either. So that's that. Then I get plus z, because I get z times 1, and if I do any other multiplication, I get terms of order higher than z. Then we get z squared times negative 1 plus 1/2. Well, that's because we've got 1 times negative z squared giving us the negative 1/2. Z squared over 2 times 1 gives us the 1/2, and any other product will not give us a z squared, so we always look for exponents that add up to 2 in this case. For z cubed, we look for exponents that add up to 3, and so that would be z times negative z squared giving us the negative 1. Z squared times anything over here doesn't give us a cube, and 1 times anything over here doesn't give us a cube either. Then we get z cubed over 6 times 1 giving us the 1 over 6. And once we multiply with z to the 4th, of course, we don't get z cubes anymore. Z to the 4th, well, let's see. I have the 1 times the z to the 4th, and that gives us the 1. I've got the z times anything over here doesn't give us a z to the 4th, so we don't get that. Z squared over 2 times negative z squared gives us negative 1/2 z to the 4th. That gives us a negative 1/2 here. But z squared over 2 times anything else over here doesn't give us z to the 4th. Z cubed times anything over here doesn't give us z to the 4th. And then we have z to the 4th over 24 times 1. That gives us the 1 over 24. And z to the 5th and so on gives us stuff that has a power that is too high. And then we can just simply clean that up. So this, first of all, keeps going. And then we get, well, 1 plus z squared negative 1 times negative 1 plus 1/2 is negative 1/2. So that would be minus 1/2 z squared. Minus 1/2 z squared. Then we have minus 5/6 z cubed. And that works out. And then we've got 1 minus 1/2 is 12 over 24 plus 1 over 24 is plus 13 over 24 z to the 4th. And that keeps going like that. Typically, it is extremely hard, if not impossible, I think typically impossible, to really find a pattern in these coefficients. So typically people are looking for the first couple of coefficients in these homework problems. If I want to expand 1 over cosine z into a power series around 0, that's where I would have to divide. And because the cosine of z is 1 minus x squared over 2 plus x squared x to the 4th over 24, which is the 4 factorial. And if you look at x to the 6th over 6 factorial, well, 5 times 24 is 120. Multiply that by 6, you get the 720. We can obtain the first few terms of the expansions by generalizing the division of polynomials. We know that 1 over cosine z will be analytic in a neighborhood of the origin because this is a valid definition and we have the quotient rule available, of course. But in order to get the coefficients, we will not get the full expansion, and the algorithm will also show that getting the full expansion by straightforward division would be a bit, here's where I'm definitely understating the case, but it would be a bit much to hope for. Okay, let's take a look at the expansion. 1 divided by 1 minus z squared plus z to the 4th over 24 minus z to the 6th over 720. Well, 1 times 1 is 1, so 1 goes into 1 1 times. And now we have to subtract 1 times all that. So we get subtract minus 1 minus z squared over 2 plus z to the 4th over 24 minus z to the 6th over 720. And that, of course, works out rather nicely because only the signs change, right? We get them. The minus becomes a plus, the plus becomes a minus, the minus becomes a plus, and then it just keeps going like that somehow. And I have a plus here instead of a minus, but it could be plus a negative term, so no problem there. And now I have that in order to get z squared over 2, I have to multiply 1 by z squared over 2, so I get a plus z squared over 2. Now I multiply everything with z squared over 2, and so I get z squared over 2 minus z squared over 2 times z squared over 2 would be minus z to the 4th over 4, and then we get z to the 4th over 24 times z squared over 2, which would be z to the 6th over 48, and now we do the subtraction. Of course that's going to get ugly, right? Well, the big thing is the z squared over 2 goes away, and then we have, let's see, this thing here is 6 over 24, so we get minus minus plus. 6 over 24 minus 1 over 24 is 5 over 24 times the z to the 4th. And this one, oh my goodness, I think 48 times 10 is 480, and 48 times 5 is 240, and if you add that together you get 720. So this is 15 over 48 times 720, negative 15 over 720. Then we add 1 over 720, which is negative 14 over 720, and that's negative 7 over 360, and we keep the z to the 6th, of course, so that works out. And of course we keep going like that. 1 has to be multiplied with 5z to the 4th over 24 to get 5z to the 4th over 24. And now we multiply again, we get 5z to the 4th over 24, and then 5z to the 6th over 48. And if we subtract that out, we get, well, again, a 0 here, and we obtain, oh my goodness, well, we had that 48 was 15 times 720. Okay, so we have to multiply with 15. We end up with 5 times 15, which is 75. So plus 75 over 720. And this is negative 14 over 720. 75 minus 14 is 61. So that ends up being 61 z to the 6th over 720. And of course, it just keeps on going like that because we have the 61 z to the 6 over 720 here now, and we keep doing those subtractions. Now, what you can see is that these terms get progressively smaller, and that is why, at least near 0, and that is why the power series expansion ultimately does converge. But we can also see that it's quite impossible to get a pattern here. However, what you can do as a sanity check for any of these computations is you can just go ahead and do the expansion on the real line. So let's take a look at that polynomial that we have on the previous panel, and I will put that up in red, and 1 over cosine z, cosine x is put up in blue. Well, the polynomial looks like this, and 1 over cosine x looks like this. Of course, it has a singularity at pi over 2 and at negative pi over 2, so the power series cannot be expected to converge beyond that, and so then these branches here are not being met by the power series, obviously. But other than that, hey, yeah, it does work. we did get the right result, and of course, in light of all those mistakes that I've made, for which I apologize, that is something to be really happy about. But I can stop this presentation on a note that I want to hit every so often anyway, and that is, whenever you can check yourself, do check yourself. Whenever you proofread, do proofread. Of course, that is something, whenever you can proofread, do proofread before you submit homeworks and the like. But that is something, obviously, that I also should take to heart. But here's where I can tell you from experience, as well as from what happened here, as you proofread your own work, often you don't read what you've written. You read what you think you've written, and that's what certainly happened as I proofread these slides. Sounds like today is not a very good day for me to continue, which means I'll probably continue recording on another day with more thoroughly proofread slides. But remember, if you have that option to reproofread something before you submit it, it may be a good idea to just, the night when you get the solution, when you think it works, to put your solution aside and read it again the next morning, just to make absolutely sure that everything is about as perfect as can be. Okay, with that, I guess the sermon that I should also take to heart ends right here, and I'll see you in the next presentation. Thanks a lot.